So the principles of flight. How does an airplane fly? So
It's magic.
Sometimes it feels like it, doesn't it? Well, we have these two wings here. And as the airplane flies, obviously we're moving forward through the air. The air flows over the wings, and it creates lift. Well, how does it do that? In the most basic sense, we're creating a pressure differential between the bottom of the wing and the top of the wing. So we have high pressure air underneath pushing us up, low pressure air on the top pulling us up, and that makes lift. Now, in order to do that, the wing has, most wings have a characteristic shape. We call it an airfoil. It's a little more curved on the top, it's a little more flat on the bottom. Now, on this model, you'll notice these wings are just a piece of paper. They're pretty much flat. These wings, even though they're pretty flat, I'll bet you they'll still create lift. What do you say?
Yeah, but if you throw that, it's not going to end well. Because you can see I've thrown that a few times.
Oh, yeah.
One example of how the lift works is I remember as a kid in school when we were learning about it, we'd hold a piece of paper up and we'd let it fall over, and then we'd blow on it and the back would come up.
Yep.
Because it's that whole lift principle, the air pressure on the top gets lower because it's moving faster over that bump. And it would pull the back up, and it just, for a kid, a little kid, it defies gravity. It defies what their brain thinks should be working, which is how a plane flies.
And in fact, as we talked about that, so what you're getting into is Bernoulli's principle, which talk about a bit in the book here. And that's great, but talking about Bernoulli's principle in a vacuum, so to speak, leaves a lot out.
Right, but for a kid,
exactly.
This is how a plane works, and they can actually see the lift being made.
Right.
So.
And the thing to realize, though, about Bernoulli's principle, they always talk about the curved surface on the top of the wing. The air flows faster over the top than over the bottom. We get low pressure. Well, yes, to an extent, that's true. And that is the classic explanation for how the wing creates lift. But if that was all that was going on, you have a flat piece of paper like this, or an almost flat wing like a fighter jet has, and you'd get no lift. So the other thing that's going on is, another term to introduce here, is the angle of attack. So the angle of attack is the angle between the wing and the air that's hitting the wing. So as the wing has an angle on the air, that air hits the front of the wing. Well, some of that air goes underneath the wing and will follow the bottom surface of the wing. Some of the air goes over the top of the wing and will follow the top surface of the wing. Okay? So the air underneath the wing, that's pretty simple to understand. It hits the bottom of the wing, it follows that angle downwards and gets to the back. The air on the top of the wing, now, since there's this angle here, that air would want to not be disturbed, or in relative terms, we talk about the relative wind hitting the wing, because there's not necessarily any wind, but the airplane moving through the air makes it feel like there's wind. So the relative wind on the wing would want to just keep on going straight. But once it touches that wing has an angle of attack, that air wants to adhere to the surface of the wing, because nature abhors a vacuum. So the air, you're not going to get a vacuum exactly on the top of the wing. Any lowering of pressure just makes the air want to stick to the wing even more. And as the air flows over the wing, it gets sucked downwards, so to speak, by adhering to that
the
curve of the wing, and that pulls the air down that's above it, and that pulls the air down that's above it, so on and so forth, until you get a whole area of low pressure above the wing. So, in a way, you talk about Bernoulli's principle, the curved surface of the wing producing low pressure. That's part of the story, but when you talk about it in abstract terms, it doesn't make much sense, does it? So when you think about it in terms of the air just wants to follow the top surface of the wing, and as it does that, the air gets pulled downwards. That air getting pulled downwards pulls downwards on the air above it, and above it, and above it, and that creates a whole area of low pressure.
And then because the plane's on an angle, hitting it right here is creating high pressure down here.
Exactly.
Pushing it up on its own, plus the low pressure from
Right.
the angle
So
of
you
attack.
get the high pressure from the air hitting the bottom of the wing, and when the air hits the bottom of the wing, it has to change direction to follow the bottom surface of the wing, and when
It's almost like pushing it down,
right,
which shoves it up then.
but
right?
that forcing the air to change direction on the bottom raises its pressure because that wing is pushing the air downwards, and that air pushes downward on the air below it and the air below it, and you get a whole area of high pressure below the wing. From the air being pushed downwards, you get a whole area of low pressure on the top of the wing from the air sort of sticking to the surface and pulling down on the air above it and the air above it. And since you can't really pull air apart, it's a
fluid, right?
It's a fluid. It doesn't like to get pulled apart into component parts. So what ends up happening is the pressure goes down. And if you were to get into the math of it, you would find that thinking about it that way, or thinking about it sort of the more classic way that Bernoulli's principle is explained, it's sort of two sides of the same coin. The same thing's going on. The same math still explains it. It's just how
You're throwing other multipliers in by how much you're doing this with the plane.
Exactly. And that's part of the reason why an airplane with flat wings like this model, or like an F-16, for example, well, they're not completely flat, but they're they're close enough to flat that they're
rockets with control surfaces.
Pretty much. So people learn about how a wing creates lift, and all you talk about is Bernoulli. Well, the natural question is, well, then how does a flat wing fly? And the answer is it's all about the angle of attack. So that's a little bit about creating lift. Now they have some good...
the center of pressure changes as you do that. I remember reading that, the CP.
Mm-hmm. So as you change the angle attack of the wing, a wing with zero angle of attack, well, first of all, it's probably not going to be creating much lift at all. But what lift it will create will be pretty much in the middle. As you increase the angle of attack, it moves upwards towards the leading edge, because the leading edge is where that air has to change course, and that's where you're getting most of that pressure differential applied. And we have a very good illustration here in Figure 4-7 in the Pilot's Handbook of Aeronautical Knowledge, showing just how that happens. And they show going from a angle of attack here, just as an example, of -8 degrees all the way up to an angle of attack of +10 degrees, and how the center of pressure moves as you do that, and how the amount of lift increases. Now that's all well and good, but when you get to a high enough angle of attack, that air, even though it wants to stick to the top of that wing, wants to make that corner and flow smoothly along the top of that wing. You get to a certain point, air has mass. It can't just change direction instantaneously. So as you increase the angle of attack, you get to the point where that angle is so sharp that the mass of the air just won't allow it to change course quickly enough to stick to the top of the wing. And when that happens, the airflow begins to separate from the top of the wing. You get sort of eddies and turbulent currents on the top of the wing, and that disrupts that smooth flow, and that means that the air is no longer nearly as effective at pulling down on the air on top of it and the air on top of it, but rather the air within that region where the turbulent flow starts to happen over the top of the wing sort of insulates the wing from the air above it, and therefore you don't get
that's when bad
a nice
things happen.
low pressure area on top of the wing anymore. Now you're still getting the air hitting the bottom of the wing, so it's not as if when a wing stalls you're amount of lift you're creating suddenly goes to zero instantaneously, just like that. But the amount of lift will decrease considerably. And when that happens, the airplane tends to
That's when,
lose
in
altitude.
videos I've seen, that's when the plane starts shaking.
Shaking a little bit.
'Cause it's,
And that shaking is mainly due to those eddies and back currents on the top of the wing, creating all that turbulence. And what you're actually feeling when the airplane starts to shake is all that turbulence on the top of the wing shaking those wings, and the wings shaking
Right.
shakes the fuselage, and you feel that through the seat as what we call a buffet. And that happens just before the wing stalls. And when the wing stalls, the nose will tend to drop because, as we talked about, the center of pressure, as the angle of attack increases, starts to move forward. Well, when you get that flow separation, that center of pressure tends to sort of snap back to where it was, because you're effectively your I don't want to say your angle of attack has been decreased, because your angle of attack is still the same, but the pressure differential between the top and bottom of the wings has been decreased, and therefore less pressure differential tends to move the center of pressure aft,
which pushes
and
the nose down.
or more precisely pushes the tail up, but same effect.
Pulls the nose down.
Yep. And as the nose comes down, you tend to reduce that angle of attack, and the speed tends to increase because your nose up.
Then the air sticks again.
You stall, the nose comes down, you start gaining some more speed, and the angle of attack, so you're flying along here near the stall, your angle of attack is this. Well, the relative wind is going to shift downwards somewhat too, because the airplane's falling, but the airplane's going to pitch down even more. So now the airplane's just stalled, and you see you went from an angle of attack just like this,
Mm-hmm.
and then the airplane pitches down, you go to an angle of attack more like that, and much less angle of attack. The air adheres to the wing again, and you're
Sticks back
flying
on.
again.
Yeah.
Now, the other thing that happens, wings tend to have what's called a dihedral to them. So when you
Mhm.
look at them from the front,
Yep.
they're angled up. And the reason that we do that is when the airplane banks, and you have dihedral like this, if you go into a bank, you see this wing, the wing that's on the inside of the turn is more level, the wing that's on the outside of the turn is more angled up. And the wing that's more level, more of the lift it's creating is going straight up into lifting the airplane, whereas the wing that's more at an angle, more of that lift is going sideways. And so since more of the lift on the wing that's down is directed towards lifting the airplane, and less of the lift on the wing that's up is directed toward lifting the airplane, the wings
Yep.
tend to want to level themselves.
Yep. That's why in RC world, beginner planes are always a lot of dihedral and no
Yep.
ailerons.
Exactly. But because of that dihedral, as the air flows over the wing, it tends to want to slip out towards the tip of the wing, because that dihedral, the air wants to find a way to go up. The wing is preventing the air from going up, and therefore creating that pressure differential. And so the high pressure air wants to expand into that low pressure area, but the wing is stopping it. So the air is going to move from front to back of the wing, but it's also going to try and find another way around the wing, so it's going to slip from rip to tip, from next to the fuselage out towards the tip of the wing, in order to try and find another way to get around that wing to fill in that low pressure. And as it does that, some of the air is going to spill from underneath the tip and create a little sort of tornado
Yep.
on the wingtip, and we call that a vortex on the wingtip. And you lose energy by the air forming itself into that vortex. So there's various different ways that aircraft designers have come up with to minimize that vortex on the wingtip, either through the shape of the wingtip, or sometimes they'll put what they call a winglet.
Yep.
So sort of little,
Sometimes they'll put a wing fence.
exactly,
in
yeah, a fence along the wing to prevent that air from flowing out around the end. There's different ways that they can go about it. And even on this model, you'll see the wingtips are curved. Even that helps to reduce the tip vortex, because as the air flows outward, that curved wingtip tends to cause the tip vortex to not wrap around the tip as tightly, because the tip is curving away from it.
It doesn't have anything to wrap to.
It doesn't have anything to wrap to. So it's, now that was one of the first ways that aircraft designers found to minimize tip vortexes, and that's why a lot of older airplanes have those nice rounded wingtips.
That I didn't know.
That's one of the first. Now, as aircraft design has progressed in the years since, I mean, this airplane that we have a little model here of is a Lockheed Vega that was designed around 1930. And as aircraft design has progressed in the decades since, they found all kinds of other little tricks to help minimize those tip vortexes. Winglets, fences, as you mentioned, just shaping the airfoil differently at the wingtip, different ways to minimize that. But that nice curved wingtip is one of the first solutions that people came up with, because you'll notice, like for example on the Wright Flyer, the wingtips are pretty square.
Yep.
And then by the time they got to the 1930s, they figured out if you made the wingtip round, that was one way of making it a little more efficient. And as you moved into the 1950s, 60s, into the 70s, they've discovered other ways, putting winglets on it, modifying the airfoil at the tip. So
I've seen a lot of bush planes that have curved down on the wingtips.
Curved down. That's sort of a form of a fence to help that air.
It's very subtle, but it's a little curved down.
Yeah, and that helps to sort of contain that air as it tries to flow out around the end of the wing.
Keeps it on the wing, so it keeps better lift.
Keeps it on the wing, exactly.
It makes sense.
Yep. So that's a little bit about the basics of how wings